So, good morning, everyone. If you don't know who I am, my name is Robert Underwood. I'm a PhD candidate in computer science, co-advised by Dr. Calhoun. Today I'm going to be talking about a library that I wrote while I was working at Argonne National Lab called LibPressio. It's a library used for compression, and since a lot of you guys are doing compression-related research in some way, shape, or form, it's something that I think could potentially be useful to you all. So let's begin with an overview of what LibPressio is and what problems it solves. So if you've done anything with compression libraries so far, one of the first things that you're going to notice is that every single compression library that you use, whether it's ZFP or BLASK or SZ or gzip, they all have completely different APIs. Those APIs don't expect arguments to be in the same order. They don't expect types to be the same. They don't support all of the same types. And frankly, it's kind of a mess. It's a real pain to learn how to use it correctly. Like, just for example, one common mistake that I made a lot was ZFP and SZ, for example, expect dimension information to be passed in opposite orders. So ZFP expects it in Fortran order, SZ expects it in C order. So all of these tiny little things really start to add up into an interface that's kind of hard to use. This has meant that there's been work that's been duplicated between different lossy compressors like HDF5 filters, things of that sort, because there's not one interface across all of the compressors to implement these kinds of tools. And that's really led to a lack of cross-pollination in the research space of people doing research that compares across a large number of compressors, simply because the effort to use all of the different compressors is actually quite large. So what is LibPressio? Fundamentally, LibPressio is a generic abstraction for lossy and lossless compression of dense tensors and the measurement thereof. Does anybody not know what a tensor is? So a tensor is a multi-dimensional matrix. So you're probably used to matrices from linear algebra. They're usually 2D. A tensor is a generalization of that, which is n-dimensional, and the measurement thereof. Over the existing interfaces that you may have used, it provides a simple, or at least I think it's a simple and consistent API. So you have the same ordering of the dimension information, the same way that you pass type information across all of the different compressors that LibPressio supports. And it gives you an abstraction that you can use to collaborate with people regardless of what kinds of compressors they're using. So what kinds of compressor technologies does it already support? It supports image compression through ImageMagick, so that's a wide number of different image formats. Lossless compression through BLASK, which provides you all of kind of the standard old lossless compression algorithms in an optimized form. The FPZip floating point lossless compressor, I believe it also has an air-bounded mode. And then air-bounded lossy compression through SZ, ZFP, and MGuard. In addition to that, you've probably written your own little code about a half dozen times to compute things like compression ratios or compression bandwidths, and making sure that you're using the right timing APIs and not the wrong timing APIs. LibPressio simplifies all of this and provides interfaces for computing these basic measurements about how well your compression or decompression performance was. So how simple is this API? It fits on one slide. Now, this looks like a lot right now. Don't worry, we're about to go through this a total of 3 times. So this is the first of 3 times. So what have I done with this? I've used it to write a generic command line interface that works for all of the different error-bounded lossy compressors, as well as the other ones supported by that. I've written language bindings for both Python and Julia. I've written a automatic tuning framework, which has been published in IPDPS, or will be in May. So that's coming along soon. And then I'm also working on a second revision of that with some pretty substantial performance improvements. I've also written a distributed benchmarking framework, which basically allows you to run a bunch of experiments on compressing and decompressing files and how to spread that work over a cluster like Palmetto using MPI. So now we're going to move into the tutorial phase of this presentation, where I'm going to show you how to use LibPressio in a pretty simple example, but hopefully one that gives you an idea of what kinds of things that you can do with it. So you can go back to the documentation, read more, and learn how to actually use this at a more detailed level. So the first big thing that you're going to run into is how do you install this thing. So there is a formal way that you would install this if you're trying to get it installed on a system. I think that way is actually reasonably well documented in the README for the project using CMake. However, if you're like, I'm a little lazy, or I don't want to learn how to use CMake, this kind of 4-line Docker command that, as of Friday, is working again, that will allow you to install a Docker container, which will give you all of the dependencies, all of the various libraries that you need, and configure the library in such a way that it's as usable as possible. And then you can then mount, for example, your own data files in from your home system. So it's basically gives you a clean environment where you can do your experiments from while still preserving all of the stuff on your home system and not contaminating it with any of the LibPressio dependencies. So what's the goal of this tutorial? So the goal of this tutorial is to write a small program in C that will compress data using the SZ error-bounded lossy compressor in 10 minutes or less. So this is something that's actually reasonably useful and something that I hope will teach you some of what LibPressio has to offer as far as an API along the way. So I want to begin with a broad overview of the 5 major components in LibPressio. So these are 5 C structures that you're going to be using again and again and again. So the first one is called pressio. This is kind of a handle to the library as a whole. It handles things like getting references to the specific compressors that you might want to use. Like if you wanted to use ZFP, that's how you would get access to the ZFP compressor. Pressio options, which represents the configuration of, or the options of one or more compressor. So basically, it's a set of ways to run a particular compressor or set of compressors. Pressio data is the way that LibPressio refers to the dense tensors that we talked about earlier, and there's a bunch of different ways that it can do that. Pressio compressor is an actual instance of a compressor like SZ or ZFP. And then Pressio metrics is a tooling interface. As we walk through this example, I'm not going to talk about the tooling interface at first. We'll come back to that one at the end. But basically, that's how you can measure different things about your compressor, and it's a fairly extensible way of doing so. So now I want to go back to that one slide with a lot of code on it and kind of walk through at a high level what this code is doing. So the first thing that we see is we include some files, standard C kind of stuff. Then we're going to get an instance of the compressor. We're going to configure, validate, and assign the options. We're going to read in an input buffer, create some output buffers, compress and decompress the data, and then free the memory. That's a pretty straightforward process. And then what's nice about LibPressio is regardless of what compressor you use, these 7 or so steps pretty much remain exactly the same, and you pretty much do them exactly in order. So first thing that we need to do is we need to include the required headers that we want to use for whatever we're doing. So the first header that I want to talk about is LibPressio.h. So LibPressio.h pulls in all of the major definitions that you're going to need in order to compress, decompress, load in data. All of those sorts of things are in LibPressio.h. There's also, however, LibPressio extensions. They go in the LibPressio_ext directory. So what's the difference between an extension and the main library? Well, the main difference between extensions and the main library is the stability guarantee that I offer you. So if you write your code using only LibPressio.h, I make reasonably strong guarantees that I'm not going to break your code by a subsequent change that I make to the library. Whereas if you use the code in LibPressio_ext, these are newer features or maybe features that aren't quite as central to the purpose of the library, whose APIs may change more often. 2 major categories of extensions that you should be aware of at this point are I/O, which are basically the interfaces you use to read in files, HDF5 things into Pressio data structures in an easier way than the interface that's provided by default, as well as compressors, which is where for particular compressors that need additional C symbols in order to really be able to use them effectively, that's where they live, is in the compressors header. So once we've done that, we need to get an instance of the Pressio structure. Doing so is pretty easy. We just call Pressio instance. This gives you a new handle to the Pressio library. Each handle can provide its own error handling, so they're independent in terms of error handling. You use it to get and release instances of particular compressors. You can query the version of LibPressio. You can query what set of compressors have been configured to use LibPressio, so kind of a broad suite of things relating to general management stuff lives in this area. Once we've done that, we need to configure a compressor. I want to draw a distinction here between options and configuration. So an option is a runtime setting of a compressor. So something that you're going to change, like an air bound or maybe a compression level if you're used to using lossless compression. So those kinds of things are options. Configuration is immutable compile time configurations of libraries. For example, in SZ, there's a time series pound define that you may enable or disable at compile time. And that actually impacts how it compresses certain kinds of multidimensional data structures. So if you wanted to query those kinds of properties, you would do so using configuration. One thing that this adds over some of the other interfaces that you might see is it allows you to introspect what options happen to exist. So by introspection, I mean you can query, for example, the fact that does this set of options have an SZ airbound mode, or does it have an SZ relative airbound? So you can kind of query for the existence or non-existence of particular settings and ask things like, what are their type? I'm not showing the code to do this right here, but you should know that it exists. So when you're writing more general code that's using multiple different compressors, you know that this exists and how to use it. You also can get, set, and what I call cast option values. So for example, if you have an airbound and most of the compressors use a double for airbound, but ZFP for particular air modes uses an integer, it will automatically do the appropriate conversions for you as if you had just written the number into the code. It also allows you to validate options that you're using the compressors correctly. So once you've configured the compressor by getting a configuration from the compressor, setting the specific things that you care about, and then setting the compressor's new configuration setting, it's time to load in some data. So I've kind of demonstrated here how to read in data from files. So here we're reading in a file from the Hurricane dataset. To do so, we first created a description that describes some metadata properties of the file, including its type. That's the pressio float D type. 3, which is the dimensionality of the data, so it's 3-dimensional data, and then the dimensions are dims provided in Fortran major order. Okay. Next, we're going to create the output buffers. So LibPressio expects that you have 2 output buffers, one for the compressed data and one for the decompressed data. One thing that I want to point out here is that we're using new empty here, and we're using new empty up here, and then we're using new owning right here. So what's the difference between new empty and new owning? New owning is effectively going to do something like a malloc underneath. It's going to allocate some contiguous range of memory that you can then put values into at a later time. It's not going to initialize those values like calloc would. It's not going to do any of those kinds of things. It's just going to allocate you some memory such that it can be freed later. New empty actually doesn't do an allocation. It's just storing some metadata information such that other compressor functions and the compressors themselves can query, like, what type is this data that I'm expecting to have, or how big is the area that I have to output it. But since it's not doing a memory allocation, the compressor can then come behind you and allocate exactly how much memory it needs for whatever task. Other things that you can do with the data interface is you can query things like, what's the type of this data, how big is it in bytes, how big is it in elements, what are the values that are in this data, so you can get pointers to the actual values. And you can also query whether or not a data buffer is owning. What I mean by owning is basically, is this data structure responsible for freeing itself, or is some other data structure responsible for ultimately freeing the data that it represents? This interface also provides a set of functionality to extend this. So for example, if you wanted to do immapped back files as a Pressio data structure, there are interfaces within LibPressio to add that kind of support. But again, I'm not going to cover those today. Then compress and decompress. I'm not going to spend much time here, but it's basically a very simple interface for compressing and decompressing. Other things you can ask the compressor for are the version of the particular compressor plugin that you're using. It does a bunch of stuff for error handling. So for example, if you pass an unsupported data type, it will give you human readable error messages for what exactly you did wrong. It also is how you're going to configure the tooling interface when we get to that in a moment. Finally, we're going to have to free the memory. Any good C or Fortran programmer is used to freeing memory. Basically, you're going to call pressio data free for each of the data buffers. You may notice that we're not calling pressio data free on description. Okay, so why aren't we calling pressio data free on the description that we saw earlier? Remember, description is the metadata that we passed to input data when we read in the input data file. Well, that's because LibPressio tries to implement move semantics where they make sense. So what I mean by move semantics is that it detects that you're using this in a context in which you're unlikely to use the pointer again, and it's going to take ownership of that memory and be responsible for freeing it on your behalf. And I've documented very carefully in the documentation when things take ownership and when things do not take ownership. Pressio options free is for freeing the configuration that you've made for this particular compressor. Pressio compressor release is responsible for releasing the compressor. So what's the difference between release and free? So the difference between release and free, release is decrementing a reference count. Free is doing the equivalent of calling free. So why is that important? So if you've used SZ for any length of time, you've probably stumbled across the fact that SZ uses a set of global variables for certain aspects of its configuration. If you try to free the memory corresponding to those global variables while someone still has a reference to the SZ compressor, you will get horrible undefined behavior. A seg fault is probably the nicest thing that will happen to you. Given that you don't want that to happen, LibPressio actually takes care of remembering whether or not you need to release something in terms of actually freeing it, or if they're kind of codependent like they are in SZ, and you need to keep them around until the last one is actually gone. Once you're finally done, you call pressio release, and you can figure out all the remaining memory using the library. I told you I'd very briefly talk about the tooling interface. So here we're getting the compression ratio as well as some timing statistics. We do that by specifying the size and the time modules there in the metric IDs. We then get references to those modules in a way that LibPressio can use them, and we configure our compressor to use those metrics. After we've done that, we can do compression and decompression, or whatever other APIs we may want to call. Then, using the same interface we use to get things out of configurations, we can also use to get metrics results. So for this case, we're getting the compression ratio. Once we've gotten the compression ratio, you can treat it like any other C thing that you're used to. When you're done, make sure to free the metrics object. So what else is there? So there's an entire C++ interface that's primarily used for writing extensions. Remember I talked about the distinction between stable and unstable. The C++ interface is very unstable. We provide the ability to add new custom compressors. For example, if you need to work with T-Thresh or some other compressor that I don't currently support, writing new compressors is relatively easy. It's one C++ class. You can also use this to write meta compressors. That's how I'm writing my auto-tuning framework, is as a meta compressor. So it implements the same interface as the compressor, but it's actually going to call a different compressor in order to actually do its work. So you can see how you can kind of stack these potentially in a very powerful way because they're inherently composable. You can add support for custom metrics that you may be interested in. If you need performance, there's a C or a C++ interface for hooking the individual functions that you might need to call. If you're more interested in like the data analysis side, there's also an external metric plugin that allows you to run Python scripts or Bash scripts or R scripts or whatever other script that you might want to run to analyze your data. If you've run into HDF5 files so far in your research, I also support using HDF5 files, and it will automatically detect all of the type and dimensionality information we talked about earlier. But ultimately, I'm excited to see with whatever you guys come up with to do with this library. I'm more than happy to answer any questions, and John has asked me to kind of provide some feedback where you guys might be able to use this in your research as we go through the meeting today. So thank you for your time. Does anybody have any questions?